Hello, it's time to continue with Module 11 on regression analysis. And we're going to start taking up hypothesis testing and the t-test. Let's go back for a moment to our population regression equation. E of y equals beta 0 plus beta 1x. Notice, of course, if this slope term is equal to 0, and we looked at this graphically earlier, if that slope term is equal to 0, then there is no relationship between x and y, or at least no linear relationship. So one of the hypothesis tests we're going to be interested in is, can we conclude that the slope is 0 or not? A slope of 0 implies no relationship. Now there's two different kinds of tests called significant tests in simple regression. There's the t-test and the f-test. The t-test can be used to test the significance of the slope term, which is what we're going to be interested in first. In multiple regression, where you have more than one independent variable, there's an f-test that can test the overall level of significance of all the regression coefficients. But in simple regression, when you have only one variable, the f-test really gives you the same results as the t-test. So while we will look at both of them, they're going to give us the same results here in simple regression. Now the mathematics of these tests gets a little bit complex. And once again, while we'll go through the math, we'll show you later how to get most of these results either on your computer, or we'll also show you an Excel output and how to read the results that you need. Both tests, whether it's the t or the f test, are going to require that we have an estimate of sigma squared, where sigma squared is the variance of the error term epsilon in the population model. And the way we're going to estimate that variance is by using something we'll call s squared here, which is also called MSE, which stands for the mean square error. And in mathematics, that's equal to SSE divided by n minus 2. You'll remember that we had SSE, the unexplained variation, earlier in the last module, or in the last part of this module. If you take SSE and divide it by n minus 2, because that's actually can be shown to be the degrees of freedom in SSE, you get what's called MSE, the mean square error. If you take the square root of s squared, of course, you get s. And s is sometimes called the standard error of the estimate. So s is the square root of SSE over n minus 2. In the problem we've been doing, the grades and study hours example, if you go back a little bit in the presentation, you will remember that we had an SSE of 398.25. N minus 2 is 4. We had 6 observations in our regression, so n minus 2 is 4. So 9.98 would be S, our estimate of sigma. Now let's go to the t-test on the slope term. And again, there'll be several things we have to develop before we get to the actual hypothesis test. As usual, if you're doing a t-test on a slope term, there's 3 different forms of the hypotheses. You can have a two-sided test, a one-sided right tail test, or a one-sided left tail test. We're going to focus just on the two-sided test for now. There is a reason for that. When we get to the f-test, it can only be used for the two-sided test. And so just to keep the two examples consistent, we'll use a two-sided test for right now. Of course, remember that beta 1 is the true slope of the population regression line. That's being estimated now by B1. Like always, B1 is a statistic that is a random variable, and it has a sampling distribution. In other words, the slope term that we got is only one slope out of a very large number that we could have gotten had we had a different set of n observations. If you'll recall from a much earlier module, I usually argued that there's always 3 things we need to know about a sampling distribution: its mean, its standard deviation, and its shape. Its mean is fairly simple. The expected value of B1 is equal to beta 1, which just says that B1 is an unbiased estimator of beta 1. The standard deviation of the slope term, sigma B1, is equal to sigma, which remember is the standard deviation of the error term, over the square root of x minus x bar squared. And under the assumptions of the regression model, which we really haven't gone into in depth yet, the distribution of B1 will be normal. Now, in that formula for the standard deviation that we had a minute ago, sigma B1, we don't know sigma B1 largely because, of course, we don't know sigma, the true standard deviation of the error term. But we did have an estimate of it that we gave you just a minute ago. Remember, we're going to estimate sigma with S, where S is the square root of n SSE over n minus 2. We will use that in the numerator here for our estimated standard error of the slope term. The denominator here might look a little familiar to you. The square root of the sum of x minus x bar squared is actually the square root of the denominator of the slope term. And we'll take a look at that in a moment. Now we already have S. We calculated that from our grades and hours of study example to be 9.98. And as I was just pointing out, the denominator of SB1, this term, should look a little familiar to you. Let's jump back to an earlier slide. Remember when we did the slope B1, look at that denominator. The only difference is I don't have a square root sign here, which I do have back here. So this denominator is just the square root of what we got in the denominator of the slope term. If you go back to the actual calculation of the slope term, here was the final calculation. That denominator was 52. So I know now that the denominator here is just the square root of 52. Again, as I said, some of the calculations get a little complex, but a lot of the things we've already calculated along the way. So that gives us 1.38. Remember what we're calculating here. We're calculating the estimated standard error of the slope term, SB1. Now let's get back to hypothesis testing itself. Our test statistic is going to be a t-statistic. It should look kind of familiar to you in a lot of ways. You take your best estimate, B1, you subtract the hypothesized value, and since the most common null hypothesis is going to be that beta 1 is 0, that's going to just drop out of the formula. And you divide by the standard error, the standard deviation of B1. As I just said, if we're testing a hypothesis, beta 1 equals 0, that drops out, and we're left with just this formula down here. The t-statistic is simply B1 over its standard error. This happens to be a t-statistic with n minus 2 degrees of freedom. Now let's go through our usual steps of hypothesis testing. I'm going to do a two-sided test. Beta 1 is 0, beta 1 is not 0. Let's use a 5% alpha level. Calculate your test statistic, B1 over SB1. Again, in the example we've been doing, the grades and hours of study example, B1 was 4.807, and we just finished calculating SB1 as 1.38. That gives us a t-statistic of about 3.48. If we're using the critical value approach, we'd have to go to the t-table and get our critical t-values. If you do that with 4 degrees of freedom and a two-tailed test, we would reject the null hypothesis if we get a t-value above 2.776 or below negative 2.776. Since our t-value of 3.483 exceeds 2.776, we reject the null. And therefore we conclude that there is a significant relationship between grades and study hours. If we wanted instead to use the p-value approach, remember our decision rule, as always, in the p-value approach is to reject the null if the p-value is less than alpha. Since it's a two-sided test, you have to take the probability that t is above your calculated t of 3.48 and double it for the other side. Again, if you're using a table, you'll just have to approximate or estimate in the table. The best you can do with the table is say it's somewhere between 0.02 and 0.05. Doing it on a calculator, you'll get 0.0254 as the p-value. Your decision, as before, since the p-value is less than alpha, we reject the null. And by rejecting the null, we are again concluding that there is a significant relationship between these two variables. If you want to do this t-test on a TI-83 or 84 calculator, first put your two variables in two lists. I've got x in L1 and y in L2. Press your Stat button, scroll over to Tests, and scroll down until you get to one called Lin Regression t-test. Standing again for Linear Regression t-test. On my calculator, that happens to be letter F. Hit Enter. It wants your x variable first. It wants to know where your x variable is, so tell it what list with your x variable. Then it asks for your y variable. Put in the list for your y variable. You can leave the frequency count at 1. Then it needs to know the form of your hypotheses. Is it a two-sided or one-sided test? Choose the two-sided option. Something for REGEQ, which actually is a storage place for your regression equation. You can just leave that blank. And then go to Calculate and hit Enter. It's going to give you your t-statistic, which we had a minute ago as just about 3.48. Might be off slightly on your calculator because of rounding. Actually, the calculator will be more accurate. It'll give you your p-value, 0.0254, for the hypothesis test on the slope term. If you scroll down, it'll give you your coefficients. Now it labels the coefficients A and B rather than B0 and B1. A is the intercept term, 41.34. B is the slope term, 4.807. It gives you the standard error of the estimate, S, 9.98. Finally, you'll get to R squared, the coefficient of determination, 0.751. And it gives you R, the correlation coefficient of 0.866. Quite a bit easier than doing the calculations by hand. And that's all for this part. In the next part, we'll take a look at what's called the F-test, and we'll show you how to do this on Excel.